All right, we've had a few short videos of the last one. Today, not so much. This one will be a little bit longer. So what we're going to get into is binomial random variables. And we're going to be, basically today, we're going to be doing these two parts. Next video will be this, and then the last video before the review will be that one. So, if you read this, this is one of the t-shirts that math teachers like to get because they think it's funny. There are two types of people in the world, those who understand binary and those who don't. And everybody's like, but that's 10. But if you want, binary is yes or no. Binary. On or off, or in this case, 0 or 1. And so if you actually know binary, that's actually the number 2. And what we're going to be doing today are binomials. So it's binary situations, yes or no things. So binomial settings. So there's certain conditions that we have to get a binomial setting. There's a fixed number of trials. There's a number of successes we're looking at. The probabilities are independent and do not change. And it's a binary situation. And so a binomial settings arise. There's basically 4 criteria that need to be met for a situation to be a binomial setting. You can pause this and write all this down. But the binomial setting is, we use the acronym BINS. You got to check the BINS to make sure it's binary. So is it binary? Is it a yes or no questions? Or in this case, success or failure? And you'll notice success is in quotation marks because success just means yes or no. It doesn't necessarily mean good. Right. Independent. Are these things independent? Does the probability of, going back to our definition of independence, does the probability of B given A equal the probability of A, or probability of B, sorry? Does what happens in one thing affect the next one? Is there a set number of trials fixed in advance? And on each trial, the probability of success must be the same. And so these two are kind of linked. But those are the conditions. BINS. We got to check the BINS. So, tell me. Think about it. Think about BINS. Check each one, the B, the I, the N, and the S, for each one of these 3. Pause it, think about it, and then I'll give you the answers. All right, so for A, is it binary? Yes. You roll a fair die. You either roll a 6 or you don't. Is it independent? Yes. We're knowing the outcome of past rolls doesn't provide any future rolls. Number. Is there a set number of trials? Yes. It says we're going to roll it 10 times. And is the probability of success the same time each time? Yes, it's 1 out of 6. So that is a binomial setting. That is something that's going to be, we're going to be able to find the probability of that outcome using what's a binomial formula for binomial probabilities. So this is a binomial setting. So B, shooting a basketball 20 times from various distance on the court. Let Y number of the shots being made. Is it binomial? Yeah, you either make the basket or you don't. Is it independent? Well, we're going to assume that what happens on one shot doesn't happen on the next one. That's reasonable. Is the number of trials set? Yes. N is fixed. And is the chance of success in each shot the same? And the answer is negatory. So because shooting a 3-pointer and shooting a layup do not give you the same probability of success, so this is not a binomial setting. C is not a binomial setting because it's not binary. C equals color. It's not a yes or no, a success or a failure type of question. So that's how we test if something's a binomial setting. So then we have a binomial random variable, and that's something, once again, that is a random variable in a binomial setting. So if we toss a coin and we get heads or tails, probability of success each time is 0.5, the number of heads, the number of tails, and it follows if we were to actually do this, 10 times, we'd actually see a binomial distribution of all the different outcomes. You could have, if we flip the coin, say 10 times, you could have 1 heads, 2 heads, 3 heads, 4 heads, 5 heads, 6 heads, 7 heads, 8 heads, 9 heads, or 10 heads, or 0 heads. And so what we'll see is we'll see a number of most likely. 5 is the most likely, but it will follow a distribution. And we could do a tree diagram and work that out. But what's nice is that we're going to come up with a formula that will do it for us. And so let's talk about that formula. First of all, if you see this, what does that mean? Right? You read that as 5 factorial. It is not 5! Right? It's 5 factorial. And so 5 factorial is 5 times 4 times 3 times 2 times 1. 7 factorial then would be 7 times 5, 7 times 6 times 5 times 4 times 3 times 2 times 1. And if you've taken any upper level math classes, you'll get this trick where 7 factorial over 5 factorial is 7 times 6 times 5 factorial over 5 factorial. Because think about it. After the 6, we just go down from 5, but that's what 5 factorial is. And so you can do those by hand without having to multiply them all the way out. Factorials those numbers get big in a hurry. They get big in a hurry. And so this is an example in your book. You can follow along and read your textbook to do this. But basically what they did is they said they did a binomial setting. A child with a particular pair of parents has a probability of 0.25 of having type O blood. If you're taking biology, the allele for type O blood is the recessive. And so what we're probably talking about here is where neither parent has type O bloods, but they're both carriers of the allele. And so there's only a 1 in 4 chance, if you do your Punnett square, that they'll get the type O blood. If the parents have 5 children, the count X is the number of kids that will have type O blood. And so we can do this, and you could do a tree diagram for this or something like that, and you would see that you get a crazy formula here. So what's the probability that you would get 2 kids with exactly 2 kids with type O blood? And so the probability of success times probability of success times probability of failure times probability of failure times probability of failure is this right here. Right? 2 successes, 3 failures. However, this could happen a couple different patterns. You could have SS, FF, and so you start seeing all these different arrangements. And so you get, if you do this and you work out all the math and you decode it all, you'll get here. And if you want to come in, I can come in after school and decode it for you. For now, let's just move forward and say that that's how it worked. And this is the number of arrangements in a binomial setting is last time there was 2 successes and 3 failures. So the number of arrangements is going to be p to the, in this last one, exactly 2 times, oh sorry, so the probability of success in our previous example was 0.25. So that's going to be 0.25 squared times 1 minus 0.25, which is the times to the 5 minus 2. And you'll see that that's exactly what's written here. And the number of ways of arranging k-successing among m observations is the binomial coefficient, which is, you will also know as a combination. Combination. I don't know, I can't spell. So it's a combination. And if you remember from Algebra 2, you can do that on your calculator. This is the formula for combination. This is the way it's written. And so this would be, our previous example was that. Because it was 2 successes out of 5. So that's 5 factorial over 2 factorial times 3 factorial. And so if we want to simplify that, that's 5 times 4 times 3 factorial. 2 factorial is just 2, because it's 2 times 1 over 3 factorial. That cancels, and we get 20 over 2, which is 10. Which, if we go back, you will see is this number right here. And so that's the coefficient. That's the number of, there's 10 different ways that that can be arranged. And so what we'll find is that if you can put this all together and you get a new formula. And this is on the formula sheet for the SOL. But this is the coefficient, and this is the probability. And this is the binomial coefficient. And then you just plug everything in. So let's do one of those. But write down that formula here. Let me erase my writing on it so it's a little bit clearer. Is need to have that down, and then I'll walk you through a problem like that. You can pause if you need be. All right, whoops, sorry, some of this is supposed to be covered up. All right, so suppose that a child of a particular parent has a 0.25 chance of having type O blood. Find the probability that exactly 3 of the children have type O blood. So what you would do is you let X be the number of children with type O blood. And so it's just this. It's 5, a combination of 5, pick 3, is how you would say that. 0.25 to the 3 and 0.75 to the 2. And if you do that all the way out, you get 0.087. So there is a 8.7% chance that they would have 3 kids with type O blood. Should the parents be surprised if more than 3 of their children have type O blood? Surprised a little bit. To do that, you would do the probability of greater than 3 is the probability of 4 and the probability of 5. So let's look at the probability of that. The probability, and you would do that, you'd add the 2 pieces together, and you get a 0.015. And yeah, they should be really surprised, because it's, once again, our threshold is that 5%. So it was less, if something happens that has a less than a 5% chance of happening, we should be surprised. I don't even know what bell that is, but that's okay. So that's it on this. Look through the examples in your book, the binomial probabilities. We need to know how to do them by hand, but in class I'm going to teach you some other ways to do it, but practice one of these, and we'll practice a bunch of these in class. The key thing here is make sure you have this formula and make sure you understand how to evaluate that. All right. Everybody have a nice break.